All right, good afternoon, everyone. I'm sorry we're starting a little late, a little technical difficulties getting the video to work. Welcome. My name is Mark Seager. I'm the tech rep for Intel and Open Compute Platform Foundation, and just started this about 3-4 months ago. Learned a lot in that period of time. I'm also the CTO for the HPC ecosystem and the Data Center Solution Group. And what I'd like to talk about today is the way that we're approaching collaboration and innovation in the context of the open OCP community. Let's see if this is working. Slide. Go to the next one. There we go. So this is a slide that Jason showed this morning, and it's really foundational in terms of the way that we think about the cloud service environment, but also the other things that are associated with that, the Internet of Things and the sources of data and the scale of the thing and the new generation of services that will be enabled with 5G. In customer engagement after customer engagement, what we're seeing is what you would think of as traditional industries like retail or manufacturing or even education and government labs are transforming themselves into digital entities, with the digital element becoming a key part of the business value that those companies or organizations are creating. And the things that go around that are really the ways that value is, creation gathers data and creates services that go back out. I was flying back from Germany last night and I saw a very interesting segment about how the retail industry is transforming. And Amazon actually got a little bit wrong. It's not just going to be cloud services and online purchasing that's going to drive behavior. But it's really going to drive behavior is brick and mortar stores with a completely different interface to it, a completely different experience to that. And there's actually a process of creating an experience in those digital, in those physical stores that creates dopamine in your brain that makes you want to come back and buy more. And then the way that the retail sector is integrating the cloud infrastructure into providing those services is, yes, you can order it online, and then you can pick it up in the store, or you can have it mailed to you, of course. Or you can, if you're a bank, as you walk by the bank and they detect, your bank app detects where you are, they'll send a text message saying, hey, that credit card you ordered is in this bank, you can pick it up. It's a completely different way of interacting. And we're seeing large manufacturing companies like GE make a big bet on this cloud infrastructure, saying, this is so important, we're going to invest $5 billion to create a new business unit inside GE called GE Digital. And it's going to be the industrial Internet of Things. So GE makes things like locomotives. They make gas turbines that generate electricity. They make gas turbines, better known as jet engines, that go in aircraft. And my colleagues at GE Research were telling me that they're now generating 1 terabyte of data per flight. So if you see GE engines on a jet engine, you know that they're generating 1 terabyte of data per that flight. And so what they're using that data for is to simulate that jet engine as it's actually built, so they have the high performance simulation capability to design the jet engine to optimize the fuel economy, reduce the noise and carbon monoxide and other things being ejected out the back end. And then what they're also doing is creating a digital twin of the jet engines that are actually manufactured and the airlines, the end users of those jet engines, how they actually use it. And it turns out there's a big difference in the way jet engines are used if you're flying out of Abu Dhabi airport and they have sandstorms and all that kind of stuff, versus Seattle where it's wet and lots of moisture in the air. And that changes the profile that you have to maintain those engines. And right now, the maintenance procedures are incredibly conservative, and they actually cost the airlines a whole bunch of money doing those maintenance cycles. So what GE wants to do is to simulate those jet engines and recommend to the airlines as a service a more rational maintenance schedule that's based on the actual usage of each and every jet engine. And that's the digital transformation that we're talking about here. And it has a lot of moving parts, a lot of elements to it. And the way that we think about it is that the Internet of Things, the devices out there, are as I mentioned, are creating the data and interfacing with the devices and also with people. And then those are connected back to the data center where the data is collected and analyzed and so forth and accelerated with some acceleration technologies. And then the services based on that data are then fed back out to where they're consumed on the edge and the Internet of Things. And that includes desktops for engineers designing jet engines and so forth. And so if we think about this virtuous cycle, as you have more data, there's this thing called data gravity. The more data you have, the more value that data has, the more data wants to accrete to that repository to create more data analysis capabilities and new services out of that. And that drives then the Internet of Things. And there the examples there just keep growing. So as I mentioned earlier, the data here is growing by leaps and bounds, and it's on an exponential growth curve. Usually they show the dates in linear and the amount of data in a logarithm, and then it's a straight line like that. But that really means it's a hockey stick going up like that. So there's tremendous value in cloud environments, both on-premise and in cloud service providers as a burst service or as a remote computing platform. And that's why Intel was a founding member of OCP and continues to have a continuing contribution to OCP. And some of the contributions are direct to OCP, and some of them are indirect. Here's an example of an Intel partnership with Facebook. We win Microsemi, creating the next generation NVMe device called Project Lightning. It scales really well. It's based on open hardware, based on open software. It has many flexible form factors, and we see it as a device that enables both hot and warm storage tiers. So this is an involvement that has Intel in the background, working with Facebook in the foreground to do the design and work with WeWin and Microsemi to actually manufacture the device. Now, what does Intel do in the background? We do what we call enabling, right? This is an unsung part of the Intel ecosystem where we provide a basic design material for the devices that go in there, for the processors that go in there, the networking capability, the PCIe infrastructure, all that kind of stuff, and then consult with Facebook as they do the design and work with their providers to actually complete the design, do prototypes, debug, and then launch into production. So that's not a project we lead, but it's a project that couldn't happen without Intel. So an area that from the perspective of my talk here is another contribution to the community in an enabling sense, right? This is not open source hardware here. Obviously, it's a next generation Xeon processor codenamed Skylake. But you have already seen in Jason's talk and other talks this morning, keynotes, that this processor and the Purley platform that's associated with it is forming the foundational element of the compute and storage elements of upcoming designs from Microsoft, as we heard this morning, and Facebook and others. And this next generation processor, in my view, this is an Intel speak here, is a leap ahead capability. The performance per core is 15 or more percent. New set of instructions, vector instructions, which double the floating point performance, and for machine learning, that's real important. It's got accelerated I/O. With Intel OmniBath architecture, that's a fabric that's not Ethernet. It's very high bandwidth, 12.5 gigabytes a second, very low latency, sub-microsecond latency when you go direct to the hardware. And it's also high messaging rate, hundreds of millions of messages per second. That gets integrated into the package with the processor for high-performance computing applications that require that level of performance and scalability. Now, the other thing that we're doing, and you're going to see more and more of this with every generation of Intel processors, we're adding accelerators into the chipsets and also into the processor itself. There's a technology that's been in the chipset for 2 generations now called Quick Assist technology. Basically, that's an acceleration engine in the PCH, the Southbridge chip, that offloads the encryption and decryption functionality. It also does compression, and it also does RAID calculations, erasure code type calculations. And you'll see that migrate closer to the processor in future generations. There's also advanced RAS technology. And this is really important for the hyperscale environments of the cloud service providers. It's also really important in high-performance computing systems. I was in Germany talking to some users who were contemplating building a single high-performance system that has 51,200 processors in it as a single system that needs to stay up for weeks at a time. So that RAS capability is absolutely essential. And then there's a resource director technology that is a sort of an advanced turbo boost capability that allows us to direct power around in the processor to maximize the performance of various workloads. And so this is although we won't and can't take credit for this as an OCP contribution, it really is a foundational element of a lot of other folks' designs going forward. So this is an example from another partner, Microsoft, for Project Olympus. We heard a great talk this morning about that project. And again, Intel is playing a role behind the scenes with Microsoft in their supply chain to do the designs. We gave them the Pearly reference design that was designed by Intel and is available for purchase as a standard white box server from PCSD at Intel. But that design was turned over to Microsoft and the supply chain there to modify into this form factor and to express elements of that design point that were important for Microsoft in this environment. Another one that we've done, and this is, Jason spoke about this earlier as well. This is a Adams Pass motherboard. In my previous life before Intel, I was at the Lawrence Livermore lab and bought just literally hundreds of thousands of these half-height, half-width boards that go into a 2U form factor to build high-performance computing clusters. This one is based on KNL, and it has the OmniPath fabric integrated into the processor package there. And it has 6 DIMM slots and is customized for this 2U 4-node system. It also has, in some instantiations, power or water-assisted cooling to crank up the clock rate and get the maximum performance out of this hardware. And and we have worked with Penguin Computing just about 4 miles from here to design a chassis for this, and that was submitted the motherboard was submitted, design was submitted by Intel prior to Open Summit, and so that's been submitted, and the chassis has been submitted from Penguin. So you'll be able to get an open source motherboard, high performance computing motherboard, and the chassis and have a supplier with this this element here built as a SKU that you can order as a product in the near term. The products are actually out in the market, and we're now going through the process of getting the design certified by the OCP Foundation. So I mentioned several fellow travelers in the Intel. Oops, sorry about that. In the Intel ecosystem that we're enabling. This is I don't know why it keeps doing that. Sorry about that we're enabling for OCP and RSD. And the list is growing. I got, in the last week while I was working on this talk, I got 3 updates to this thing where they added new logos. So that's an amazing ecosystem story. The thing that really amazes me when I was a customer was that you don't ever hear about this, and it has a tremendous impact. And I'll come back to that when I start talking about the software ecosystem that we're developing. So RSD is a revolution in the data center. That's focusing, not on the server or the storage system or the network, but on the rack that all of that stuff fits into, and we're beginning to see that those rack elements actually be disaggregated. And there's an infrastructure that needs to be built both on the hardware side and the software side that allows you, on a dynamic basis, application by application, VM by VM, aggregate those resources back together and provide that to a complicated workflow that may span multiple racks in a pod or multiple pods across the data center. Now, if you just think about the ecosystem enabling problem that is posed by this. When you're disaggregating a server and moving the I/O subsystem out of the server, there's a whole different set of players that are involved in the software environment, all the way from the BIOS and the firmware and a BMC, up to the layers where you gather telemetry about where the hardware is and what state it's in and what capabilities it has and so forth, and then using that through an orchestration layer to be able to figure out how to use those things and what combinations, and which may vary from OEM to OEM or ODM to ODM, and to make sure that all that works. So we actually have a large number of people out there thinking about these rack scale designs and the way that people are using them, and the way that people are architecting them into the data center at very high scale. So one of the major things that we're thinking about is the data center management, and Jason talked about this a little bit. So I'm going to take a completely different element to that. So Snap is a open telemetry framework that allows you to gather the data about the hardware and that's there in its state, but it also allows you to gather telemetry about how it's being used in anger with a workload on top of it, and then optimize that at the workload level, but also optimize it at the rack level and the data center level. On the high performance computing side, we're looking at a thing called OpenHPC, which is another community for software this time, for high-performance computing software. And there are it's sort of like OpenStack, but it's for the HPC workload as opposed to a cloud workload. There's over 60 components to that software stack. And the high-performance computing community, since Thomas Sterling invented the word Beowulf, have been working on this software stack for those 20, 25 years now, and it's quite complex. And the complexity of this thing starts with the operating system, the Linux kernel. And this is one of the things that really amazed me. When I was a customer and buying hardware, I'm going to date myself here. This is back in the mid-90s. We had a long-term relationship with Digital Equipment Corporation, and we're transitioning from Ultrix, which was their version of Unix, to Linux on their hardware, and it just broke. It just didn't work. There were problems with the virtual memory subsystem. None of the Ethernet adapters work on the management network, and if you have a flaky management network, you may as well go home for the day because it's just no fun. And my system administrator said, you know, there's this x86 processor out there. It's pretty cool. It's not as fast as that Alpha, and at that time the floating point performance was at least a factor of 2 worse, sometimes a factor of 4 worse. He says, but we're willing to give up that performance because when I plug it in, it just works. And I said, okay, prove it to me. So they built a small cluster. They put all the pieces together. They booted the Linux operating system, and lo and behold, it just worked. And I thought that was just magic. There were all these people out there in the ecosystem making all these eyes on the code, fixing bugs and stuff. And it turns out, yes, that's true, but there's another reason for that. And it turns out there's 250 people in the Open Source Technology Center working at Intel, most of them up in Hillsboro, Oregon, that work on the Linux kernel. And it turns out Intel is one of the major contributors to the Linux kernel. And over the last 2 years, we were the major contributor to the Linux kernel. How many people knew that in this room? How many? 1, 2, 3. Okay, 4 or 5 people in the room of what? A couple hundred people knew that? I mean, I didn't know that till I started working at Intel, and they sent me this slide and said, hey, talk about the Linux kernel, dude. And it's just, to me, that's just stupefying, because those kind of contributions to an open source community like OCP are seminal. This community would not be able to function without those kind of services. And so in terms of a data center software, the whole idea of managing, cores and threads and memory and I/O devices and all that stuff, that's what the Linux kernel does. But if you start thinking about, well, how are you going to manage power in a constrained environment where the processor could actually use a lot more of the TDP than it's currently using? Just to give you an example, in the high-performance computing workloads, we have a TDP of the processor, and we run Limpak, and that usually takes 85% of that TDP. And then when I ran my user applications, it was like at 30 to 40% of TDP. So 70% of that power was actually being, of the power infrastructure was actually being wasted. So Intel, because of the pressure to be more efficient in data centers and the cloud service providers, is finding ways to make sure that the processor is always up there real close to TDP. And if the workload in a single processor isn't using that full TDP, I'd sure like to be able to use that extra power in a rack to run other parts of the workload that are running red hot quicker to get them out of the way, right? And service that. So this is an extension of what you would normally think of as work that the kernel is doing that is now working at the rack level, right? And could be even at the data center level. So you need a completely different infrastructure to start thinking about that. And that's where RSD comes in, and this type of software environment is required, for that disaggregation, but also rack level optimization and data center optimization. So the other example here of how we work for within a community, there was a panel session this morning about what software providers should do to work with the OCP community. This is a different model, and I think it's very illustrative of it. This is a software stack for OpenHPC that's similar to the software stack of OpenStack. There are some significant differences, like a gang scheduler and overlay pub-sub networks and those kinds of things. There's a large set of vendors that we are enabling in this ecosystem. So this is the punchline here for that open source community. So what I was talking about with the Linux kernel and stuff, and Snap and the other stuff in Redfish and stuff, those are all open source communities that are operating independently, doing their own thing, and creating releases. And what do you do then? So you either depend on yourself or your organization or an ODM or an OEM to provide you a software stack, in this case OpenHPC or OpenStack, that is an instantiation of that. So what we've done is create a community where we can work within the community to have regular releases on the most relevant and reliable version, or RV on the end, that gets tested within the OpenHPC community, and then that can be used and downloaded by end users without support, right? So this is the Fedora model for Red Hat as opposed to Red Hat Enterprise Linux. But we're also, and OEMs and ODMs can take that software stack and make it a product and provide that as well. And that's sort of the path that RSD software is taking today. But what we also decided to do was, in HPC environments, when you're talking about systems that have 51,200 nodes in it, you really need support because every 8 hours of downtime is $1 million, right? So we're providing product support for that, either direct to the high-end customers or through our OEM and ODM channel partners that scale out in that ecosystem. It's all open source. And because we're starting to think in terms of not just the power management piece, or not just the kernel, or not just the GNU LLVM compiler infrastructure, we're thinking about it as an integrated whole, right? We're optimizing that integrated whole for the interconnect, for NVMe hardware, for the processors, both the Xeon and Xeon Phi processors, so that you get a better together story there. And now this is the fruition, I think, of, you're going to be able to build hyperscale environments, plug it in, and it's just going to work. And if it doesn't work, you can get support for it. So this was another talk I heard recently at Intel, and I go, you got to be kidding me. You guys were able to do that? This is one of those amazing things. So Python and other interpretive languages that are extensible are known to run very slowly on most hardware. And if you're trying to get high performance out of it, like for machine learning and so forth, it's slower than molasses. But the code development environment and the way that you can interact with it and run debuggers on it and stuff is very, very productive. And so people have gravitated to this and other languages like R and so forth. And so we, Intel recognized that's a trend. We need to make sure that it runs better on IA. And so we've taken a lot of effort to take versions of libraries for Python that are heavily used by numeric intensive applications called NumPy and SciPy, where there's a lot of linear algebra routines at the heart of that. And then we've figured out how to, instead of Python all the way down to the inner loops of, Limpak routines in there, replace that with MKL, which is hand-coded, highly optimized code for that. And as you can see, we're getting from 10%, a factor of 10 improvement in performance to 60, a factor of 60 to a factor of 100 times improvement. And so this is now a distribution you can get from Intel for free. It's open source software, but it plugs into MKL and MKL DNN. And we have a whole strategy for making sure that as that gets deployed as an open source contribution to the community, to the Python community, that the performance is maintained all the way to the end user. And so this is an example of that, and also the thread building blocks infrastructure that has been used for a collaborative filtering neural net calculation, where if you look at standard Fedora Python, that's the Python that's in the Fedora release from Red Hat, and look at that as the baseline performance. You can see as we add some of these lower level library technologies to that software stack, you get a very large factor, not percentage, a factor performance improvement. And so this is the Intel Better Together story that we're weaving and pushing out into the ecosystem as our contributions in those open source communities that were on the left side of the screen previously. I don't think this community, the OCP community, really understands that is a contribution that we're making that we don't get credit for within the Open Compute Project framework, and that's okay. But I just wanted to make you guys aware that there's a lot going on there behind the scenes to make sure that the experience that you have with Intel hardware and Intel software is superior. So that's my talk. Thank you very much.